Hello, people of AP Calculus. I welcome you to day 4 of Unit 7, Differential Equations. I hope everybody is doing well. I hope you got a chance to watch yesterday's video as well. So today's lesson is just going to be a continuation of kind of what we talked about yesterday, except this time we're going to be viewing this idea of finding solutions to differential equations in more contextual application problems. So first off, I do want to just give an update regarding College Board. We haven't gotten any new information yet. We're still waiting on the test dates, the official test dates. I did talk about yesterday how the fact that there will be no multiple choice questions. It will be just free response. I did speculate yesterday, since it is 45 minutes, it probably means it's going to be 3 free response questions, but that's just speculation on my part. No official announcement towards that. But I will keep you guys updated as time progresses. So let's get to today's lesson. Start off with a bell ringer. So a multiple choice question, the graph of f double prime is shown below. If f prime of 1 is equal to 0, then f prime of x is equal to 0 at x equals blank. So hopefully you try out this problem on your own first before watching this part of the video. Now, we're given the graph of f double prime. As I've told you guys in class many times before, you always want to make sure you understand the graph of what are you given. So in this case, we're given the graph of f double prime. Okay, f double prime. Now we're being asked to find something about f prime. All right, so we're given f double prime and we're being asked a question about f prime. So remember, f double prime is the derivative of f prime. Okay, so f double prime is the derivative of f prime. So we're being given the derivative of a function, and we're being asked a question about the original function. Okay, so we're given the derivative of a function, we're being asked about the original function. So hopefully that makes you think that, in other words, this is asking us to determine something about the antiderivative of f double prime. The antiderivative of f double prime. Well, let's find the antiderivative of f double prime. Okay, so the integral of f double prime, let us find it. Now we're given a graph, an absolute value graph. We have that V shape. And we can actually find this antiderivative relatively simply. Now, this antiderivative actually ends up being two separate equations, since it's two separate lines. But the only line we're actually going to focus on today, or at least for this problem, is this one right here. So we're just going to focus on that line for this problem, or that part of the graph. So we're going to find the antiderivative of that equation. Well, since it's a line, let's quickly find the equation of that line. Well, let's see. It looks to have a slope of 1 because we're going right 1, down 1, right 1, down 1. So a slope of negative 1, excuse me. Okay, so if we put it in slope-intercept form, we have y equals negative x. Okay, if you remember y equals mx plus b, the slope m goes in front of the x. And b now is our y-intercept. Well, it looks like our y-intercept for this problem is 2. So it looks like our b value is 2. So that is the equation of just that part of the graph. So just the left half of the graph. Now, I'm just focusing on the left half of the graph because of the fact that it's telling us information about x equals 1. And x equals 1 would be right here, and that's the left half of the graph. So I just want to focus on that part. So in other words, we are finding the antiderivative of negative x plus 2. So the antiderivative of negative x plus 2. Well, this shouldn't be too bad. So let's see. If we do the reverse power rule, we end up with negative x squared over 2. Okay, recall you add 1 to the exponent. Add 1 to the exponent, so it becomes a 2. And then we divide by the exponent, so we divide by 2. And now the antiderivative of 2 is just 2x. And then we do have to write that plus c since we're finding the antiderivative. Now we can actually solve for plus c. Because we are told that f prime of 1 is equal to 0. So let's solve for that. So f prime of 1 is equal to 0. So when y is equal to 0, x is equal to 1. So negative 1 half, or negative 1 squared over 2, plus 2 times 1 plus c. So let's see what we get. We get 0 is equal to negative 1 half plus 2 plus c, which would give us, let's see, so negative a half plus 2 is 3 halves. So 0 is equal to 3 halves plus c. So it looks like c is equal to negative 3 over 2. So it looks like f prime, which is the antiderivative, remember we're finding the antiderivative of f double prime, f prime is equal to negative 1 half x squared plus 2x minus 3 halves. Okay, so negative 1 half x squared plus 2x minus 3 halves. Now we're told, when does this equal to 0? When does this equal to 0? Okay, so we're trying to figure out when this is equal to 0. So I'm going to erase some of these just so that we can have some room to solving this. So I'm going to erase some of this here. Erase that, erase that. Okay. There we go. So we're trying to find when this is equal to 0. So since we're trying to find when this is equal to 0, we do want to factor this, or we can use the quadratic formula. We could do that too, but that involves a lot more calculations. So I'm going to factor out a negative 1 half out of each of these terms. Okay, so I'm going to factor out a negative 1 half out of each of these terms. So x squared, the 2x becomes a minus 4x. Now the reason it becomes that is that when you factor out a half, okay, when you factor out a half, you have to imagine that we're factoring out a half is like multiplying everything by 2. Because if you recall, if you divide by a half, which is what factoring out a term involves, if you divide by a half, that's the same thing as multiplying by the reciprocal of 1 half, which is 2. So we're multiplying each of these terms by 2 when we're factoring out a 1 half. And then the 3 halves just becomes positive 3, because if you multiply that by 2, it just becomes 3. And then obviously, since we're factoring out a negative, whatever is originally negative becomes positive. Whatever was once positive now becomes negative. So let's try to factor this out. So we have x squared. So now I'm just going to focus on x squared minus 4x plus 3. That should be a pretty simple factoring job. So x minus 1, x minus 3. What two numbers multiply to positive 3 but add up to negative 4? So what two numbers multiply to positive 3 add up to negative 4? So now we just solve. So x minus 1 is equal to 0, x minus 3 is equal to 0. So it looks like our two solutions are x is equal to 1 and 3. Well, the problem already tells us that at 1 it's equal to 0. This was asking us to find the other x value, which just so happened to be 3. So that would be our answer. So this is a good problem because it gives you the derivative of a function, f double prime in this case, and it asks you a question about the original function, which in this case was f prime, okay? So hopefully you think about the antiderivative in situations like this. So we just found the antiderivative where we took the integral of the given function. Okay, so hopefully you got the same answer. So let's move on to today's lesson. So once again, we're going to be looking at more application problems today. So kind of the same type as yesterday, just more contextual problems. So the first problem we're going to look at today has to do with this idea of half-lives of radioactive isotopes. Hopefully this is something you guys learned back in chemistry, or maybe even physics. This idea of radioactive isotopes slowly but surely, what's the word I'm looking for here, becoming less and less radioactive over time. Now the example that we're going to look at is a real life example, and it's one of Chernobyl. Now there's a link here that should be on the handout as well, so you can just copy and paste it to check out the video. It's a pretty informative video of exactly what happened at Chernobyl. Not only for those of you who don't know, Chernobyl is a very popular nuclear disaster that occurred. Chernobyl is a city in Ukraine, and the nuclear reactor basically melted down and eventually exploded, causing a lot of radioactive fallout that eventually affected not only Ukraine itself, but a lot of countries around it, including my home country of Romania as well. So you can watch the video. It's pretty interesting. I watched it last year with my students. Obviously, this year I don't have a chance to watch it with you guys in person. But I do suggest you watch it out just to get a little bit more background information, exactly what happened, and the kind of effects that it had on people during that time. So let's move on to the problem. Now, before we move on to the problem, I do want to highlight one bullet point on this slide, which is the fact that we will assume that the rate of decay, we will assume that the rate of decay is proportional to the amount of material. So we talked about this idea that when we're told that the rate of something, the rate of change is proportional to the amount of something, that means our equation is going to look something like this. So dA over dt is equal to some constant k times the material, so times A. So it looks something like that. Okay, so just keep that in mind, that is what we are going to assume for this problem. So let's get to the problem itself. So right off the bat, we do have this diagram here. This diagram just shows what kind of radioactive fallout occurred as a result of the accident around not only, let's see if I can see it here. I believe Chernobyl is right here. And then how it affected, obviously the red spots got the most intense amount of radiation fallout, and then the orange, and then the yellow, and then the lighter tan in terms of descending intensity. So suppose that 15 grams of the cesium isotope CS-137 that was released during the 1986 Chernobyl nuclear accident absorbed into the groundwater. Now, that would be really bad if it absorbed into the groundwater, because at that point, the groundwater is the water that me and you drink, and if that becomes contaminated, no amount of filtering is going to stop that from getting to us. How long will it take for the 15 grams to decay to 1 gram and become safer to drink? Note the half-life of cesium-137 is 30 years. All right, so once again, we're going to assume, as I said in the previous slide, that the rate of decay is proportional to the amount of material. Okay, so the rate of decay, so dA over dt we'll call it, so the rate of decay is proportional to the amount of material. So we'll just call that amount of material A. You can call it M, you can call it C for cesium, whatever you want. So we're asked, how long will it take for the 15 grams to decay to 1 gram and become safer to drink? So in order to answer that question, we need to find the original equation. So remember, to find the original equation, that means we have to utilize that method we talked about yesterday, separation of variables. So we got to get the variables separated on each side of the equation. So first, right off the bat, let's get the A to the other side by multiplying both sides of this by 1 over A. So let's multiply both sides of this by 1 over A. Now, multiplication by 1 over A is the same thing as division by A. So you could do that. I like to write it as multiplication by 1 over A because it just separates it from the dA on this side. I just think it's a lot more nicer when we get to this idea of finding the integral of both sides. So we got the A to the other side. Now let's get this dt to the other side, and we do that by multiplying both sides by dt. So that cancels out that dt. So now we're left with the variable separated, so 1 over A is equal to dA is equal to k dt. Now, I'm actually going to skip some steps here, only because if you recall on yesterday's lesson, we talked about how the general solution for this type of problem always ends up looking like this. A is equal to a constant c times e to the power of kt. Now, I would still advise you to try out the steps. It's very similar to the problem we did yesterday too. So try out the steps, see if you've mastered it or not. This is the answer that you should get. A is equal to a constant c times e to the power of k t. So I'm just using the fact that this is what we talked about yesterday, and so to save some time, I will skip the rest of the steps, but I would advise you to try it out just to make sure you get the same answer. Whoops, sorry about that. And actually, there should be times here. So let's see. Now, if you recall yesterday, you can solve for that constant c. You can solve for that constant c. So we are told, let's see, that the half-life of cesium-137 is 30 years. Okay, so the half-life for cesium-137 is 30 years. So we're going to use that to figure out, we're going to use that to figure out what the constant c is equal to. We're going to use that to figure out what the constant c is equal to. So let's pretend, let me see, give me a second here, 15 grams. Oh yeah, I'm sorry. So we're given 15 grams. So we're trying to figure out when those 15 grams, or I'm sorry, that's the initial amount. So that is the amount, at t is equal to 0. So that's how much we're starting out with. So solving for C. Okay? So we have 15 grams when t is equal to 0. We have 15 grams when c is equal to 0. So that means we have 15 is equal to capital C times e to the power of 0. Anything to the 0 power is 1. So it looks like capital C is 15. Okay? So now we're going to solve for K. So now this equation is now A is equal to 15e to the power of kt. Now we're going to solve for K. We're going to find out what K is equal to. And we're going to do that by using, let me just highlight it here. So we used that for that. Now we're going to use the half-life to solve for K. Use the half-life to solve for K. So 30 years, we're going to have half as much. Well, if we started with 15, after 30 years, we should have half of 15, so 7.5. So after 30 years, we should have 7.5 grams. So 7.5 is equal to 15 e to the power of k times 30. Because after 30 years, we would have half as much. So let's see what we have here. I'm going to divide both sides by 15. So 1/2 is equal to e to the 30k power. If you recall yesterday, to get rid of e, we're going to do ln of both sides to get rid of e. So ln of both sides, or the natural log of both sides. Uh-oh, sorry about that. PowerPoint crashed. Sorry about that. Now that stinks because it doesn't save it, but it's okay. I relatively remember where we were. All right. So we were solving for K. We had the amount is equal to 15e to the power of kt so far. We're solving for K right now. And we're using this information that the half-life is 30 years to solve for K. So it was 7.5 was half of that. 15e to the k times 30 because it's 30 years. Divided both sides by 15 gives us 1/2 e to the 30k power. And this is where we were going to do ln of both sides to get rid of e. Doing ln of both sides to get rid of e. Okay. So once again, e and ln cancel out. So now we're just left with ln of 1/2 is equal to 30k. So k is going to be equal to whatever ln of 1/2 divided by 30 is, which I think it's actually safer to just leave it like that. Don't approximate, especially on the AP exam. You want to use exact answer, so just leave it as ln of 1/2 over 30, and just use that answer as we do our calculation for the final answer. So now let's look at the final thing that it's asking us, which is, how long will it take for the 15 grams to decay to 1 gram? Okay, so we're trying to figure out when it's going to be equal to 1 gram. How long? So in terms of years, how many years? So what is our t value? Okay, so let's do that. Actually, let me rewrite it. So now our equation is the amount is equal to 15 e. K is ln of 1/2 over 30 times t. Sorry. Okay, so let's find out how long will it take for the 15 grams to decay to 1 gram. So how long will it take to equal 1 gram? Okay, so 15 ln of 1/2 over 30 times t. So we're trying to figure out how many years. So what is our t value? Well, let's see. If we divide both sides by 15, we get 1 over 15 e to the power of ln 1/2 30 times t. Once again, to get rid of e, you have to do ln to both sides. ln of 1/15 is equal to ln of e, ln of 1/2 over 30 times t. Oops. So this is going to cancel out. So ln of 1/15. Why is it so... Oh, whoops. 1/15 equals ln... Oh, whoops. Darn it. It's equal to ln times t. So to solve for t, we just have to divide both sides by ln of 1/2 divided by 30. Okay, so it looks like our final answer is whatever ln of 1/15 is divided by the quantity ln of 1/2 over 30. So we just put that into a calculator. So let's see what we got. We have ln of 1/15 divided by the quantity ln of 1/2 or 0.5 divided by 30. So you should get approximately 117.207. Remember, always round to three decimal places, years. On an AP exam, always round to those 3 decimal places. So that is how long it would take the groundwater to be safer to drink. So it would take a long time. So this is actually just a good, I guess, indication of how long it takes for something to not be radioactive anymore. It does take a long time. Now, thankfully, in this case, they were actually, in real life, they were actually able to avoid any groundwater contamination as a result of this nuclear accident. So they didn't have to wait hundreds of years in order for the water to be safe to drink again. All right, so a good problem. Once again, this is not your typical problem because typically your K value would be given to you in a problem like this. It's just good practice just for using that ln to get rid of E. But in terms of solving for C, that is something you would be expected to be able to do. But solving for K, that's usually a value that would be given to you in a problem like this. So let's look at the next problem. So example 2. So introducing fish. So fish are being introduced into a man-made lake. The change in the rate of fish with respect to time is directly proportional to 900 minus f, where t is measured in years. When t is equal to 0, there are 400 fish in the lake, and 3 years later, there are 600 fish in the lake. So write and solve the differential equation that describes this situation. So first, we have to find the differential equation. So we're trying to find that derivative equation, in other words. Well, we're told here that the change in the rate of fish with respect to time is directly proportional to 900 minus f. Directly proportional. So that means, the rate of change the rate of fish, the change in the rate of fish. Yeah, so df over dt is directly proportional, so 900 minus f, directly proportional means that there's just some constant out in front being multiplied. So we have to find the solution to this, so let's get to it. So let's get the variables on one side of each equation. So let's get the 900 minus f to the other side. So we're going to do that by multiplying by 900 minus f. multiplying by 100 minus f to both sides, so 1 over 900 minus f. So we're left with 1 over 900 minus f times df over dt is equal to just k. Now we get that dt to the other side, so multiply both sides by dt. Sorry about that, squeezing in here. So we have 1 over 900 minus f times df is equal to k times dt. So we got the variables on one side of each equation, or on each side of the equation. So now we're going to do the integral of both sides. So the integral. Now, the right side should be pretty self-explanatory because it's just k, so the antiderivative is just kt. Now the left side, we're going to do a little bit of substitution for the left side. So for the left side, we're going to do a little substitution. We're going to make u is equal to 900 minus f, which means that the derivative of this is just -1 because the derivative of 900 is just 0, and then the derivative of negative f is just -1. So that means du, or negative du, is equal to dt. So we've got the du by itself, so negative du is equal to dt. So now we're actually going to make the substitution. So let's see, we have the integral of 1 over u. Whoops, did I do something wrong here? It should be df, not dt. I apologize. Yeah, you got to make sure your derivatives are. So this is df, and this is df. So df and df. All right. So 1 over u times df is just negative du. So now that's just the same thing as the integral of -1 over u du. The antiderivative of 1 over u, hopefully you remember at this point, give you a few seconds, is the natural log, or ln, of the absolute value of u, which we can just turn it into, as soon as we substitute u back in, negative natural log of the absolute value of 900 minus f. So that's the left side. So if we bring it all together, it looks like we have negative natural log of the absolute value of 900 minus f is equal to, where was it? Oh yeah, kt. That's the antiderivative of k plus c. So now I just have to figure out what c is equal to. Okay, so the antiderivative of 1 over 900 minus f is the natural log, or negative natural log, absolute value of 900 minus f. And then the antiderivative of k is just kt. And then we only put the plus c on one side, because even if you put a plus c on both sides, eventually you will only have one constant. Okay, so how are we going to find out what c is equal to? Well, if you recall, we've done it before. We're going to use, we're going to use this information right here. When t is equal to 0, there are 400 fish in the lake. When t is equal to 0, there are 400 fish in the lake. So let's do that. Let's find what c is equal to. So let's see, c, so when t is equal to 0, 400 fish, so f is 400, so negative natural log 900 minus 400 is equal to k times 0 plus c. So, well, it looks like c is equal to the negative natural log of 500. Let me check. What's part B? Is part B asking us to find? Okay, no, okay. So that means, sorry about that. Natural log, 900 minus f, absolute value, is equal to kt minus the natural log, 500. Now we still have to find k, and we're going to do that by using this other piece of information, which is 3 years later, there are 600 fish in the lake. 3 years later, there's 600 fish in the lake. So let's find k now. So 600 fish, so f is 600. So now we got natural log 900 minus 600. T is equal to 3, so 3k minus the natural log of 500. So to solve for k, let's add natural log of 500 to both sides. So if I add natural log of 500 to both sides, we have negative natural log of 300 plus natural log of 500 is equal to 3k. Now we cannot, just be careful here, we cannot add the 300 and the 500. Those are two separate terms because each of them have an ln attached to them. So you cannot say it's the natural log of 800 or the natural log of 200 since it's negative. That 300, you do have to keep those separate. So now we just divide both sides by 3. Divide both sides by 3. Let me make some room here. Divide both sides by 3. And we get natural log of 500 minus natural log of 300 over 3 is equal to k. Once again, I am not approximating that. That's going to be the exact answer. You only want to approximate your final answer. So it looks like our differential equation, if we write it all out, is negative natural log of the absolute value, 900 minus f, is equal to, let's see what we got here. A k is going to be that entire thing, natural log of 500 minus natural log of 300 over 3t. Oh, running out of room here. I've got to erase this too now. Minus the natural log of 500. Now, since we're not told to get f by itself, we would just leave it like that. Otherwise, what we could have done is we could have gotten f by itself even at this point. We could have gotten f by itself, but once again, since it's not specifying here to get f by itself, just to solve it, we would just leave it like that. All right, so now let's look at B. So B asks us, find the fish population in another 3 years. Now, be careful here. Let's be careful here. So we're told that in 3 years later, the population was 600. Oh, did I make a mistake here? No, I didn't. So another 3 years would mean 6 years later from the original. 6 years later. So this would mean t is equal to 6. So at this point, we just have to plug in t for 6 and solve for f. So we have negative natural log, the absolute value of 900 minus f is equal to, what was it? Natural log of 500 minus natural log of 300 over 3 times 6 minus ln of 500. Let me just make sure I wrote that all down correctly. 500 minus 300 over 3. I think so. Okay, so now we just have to get f by itself. So let's do that. So let's see. Let's get rid of this negative first by dividing both sides by -1. So let's divide both sides by -1. Whoops, sorry. So let's divide both sides by -1. So whatever is positive becomes negative, so on and so forth. So now it becomes natural log, absolute value of 900 minus f is equal to positive ln 500 minus, this 6 and 3 just become a 2. So I'm just going to reduce this 3 and 6 to a 2. Make my life a little bit easier here. Minus 2 times the quantity ln 500 minus ln 300. All right. So remember, to get rid of ln, we have to do e to the power of both sides. And what this does, that makes that go away. And we can now write it as 900 minus f is equal to that gigantic expression. And you know what? Just for the sake of making us having to write less, let's actually evaluate that right side. Let's actually evaluate e to the power of ln 500 minus 2, parentheses, ln 500 minus ln 300. Let's see what we get. So we get 180. So it's an exact answer, which is nice. And there is a way to simplify this entire, there is a way to simplify this entire thing. Let me see if I can do it really quickly. So that's 2. That's just squared. Well, this is a calculator question anyway, so the simplifying by hand is not necessary, but there is definitely a way to make this look a lot nicer. But since you have a calculator in hand, we can just plug it in. So now f, if we just do the math, it looks like f has to be equal to, if 900 minus f has to equal to 180, that means f has to be equal to 720. So the new population after 6 years is 720 fish. Okay. Let me see. I'm pretty sure this would have looked a lot nicer had we, in part A, solved for f. So had you solved this equation for f by just getting f by itself, it probably would have made b look a little bit nicer. But we do have a calculator, so that shouldn't have been an issue. If you do want to try getting f by itself in this problem, I think that's a good side activity or side problem to do to see if you get the same answer that you would get in part B if you plug in 6 into that equation. You should. So that's how you know to get it right. So I would actually recommend, if you want a little bit more extra practice, that answer that we had, this answer that we had, try to get f by itself and then solve for c and k, and then try part B by plugging in 6 into that equation. Either way, you should still get 720. I think it's a good exercise in making sure you know how to solve for f, because that is something you might be required to do, something that I would train yourself to doing. All right, so that's example 2. Oh, there's part C, excuse me. I forgot about it. So this one asks us, find the limit as t goes to infinity of f of t. And explain what the answer means. So remember, t is time. So this is basically just asking us, if we went into the future, to infinity, okay, what would happen to the population of fish? Well, so you could do this by simply graphing this. You can literally just plug this, what was it? If you were to plug in, if you were to graph, here's from part A. If you were to graph this equation, into a calculator, you would see what's happening to f as t goes to infinity. So graph using calculator. So you would see as that goes to infinity, as we just go into the future in infinity, the limit as t goes to infinity of f of t, if I remember correctly, should be equal to 900. Yes, it should be equal to 900. So what does that mean in the context of this problem? It means as time progresses, the population of fish hits a ceiling, or a max of 900. The population of fish never gets any higher than 900 in this scenario. So that's kind of like the equilibrium point for this population of fish. At that point, it just stays relatively constant, and 900 does not go above it. So that's what it would mean in the context of the problem. As time progresses, infinitely or without bound, the population just gets closer and closer to 900. But it never goes above it. Okay, so now let's look at one last problem, Newton's law of cooling. So Newton's law of cooling states that the rate of change in the temperature of an object is proportional, that word again, to the difference between the object's temperature and the temperature of the surrounding medium. So actually, before I show you guys the equation, I want you guys to try to see if you can figure out what this sentence, or what the equation would look like for this sentence. So it says that the rate of change of the temperature is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So I would like you to pause your video at this point and try to see if you can come up with an equation that matches this description, similar to how in example 2, for part A, we found it said that the change in the rate of fish, so df over dt, is directly proportional to 900 minus f. So that's how we got df over dt is equal to k times 900 minus f. Try to do the same thing for this. So pause your video and see if you can get the same answer. So hopefully at this point you've tried it. Now you should have ended up with something like this. Now obviously your variables might not have been exactly the same, but hopefully the format was the same. So in this case we have dt sub 0 over dt is equal to k, remember proportional, so that's your proportional constant, times t sub 0 minus t sub e. So in this case, they use t sub 0 to represent the temperature of the object. So that's the object temperature, or the initial temperature, that's why they call it sub 0. And then t sub e is the temperature of the surrounding. So hopefully you got the same thing. You might not have used the exact same variables, but that's what they mean by the difference. So difference is just subtraction, difference between object's temperature and the surrounding medium. So now we're going to be using this equation for this next problem here. Oh, I forgot that I wrote it on here. All right, so example 3. So the world-famous pastry chef, Bernie D. Rose, removes a completely baked cake from an oven and places it in a room whose temperature is kept at a constant 60 degrees Fahrenheit. Using a cooking thermometer, he determines the cake cools from 100 degrees to 90 degrees in 10 minutes. The icing that is to be used for the cake cannot be applied until the cake's temperature reaches 80 degrees Fahrenheit. How much longer must Bernie wait to ice the cake? So the temperature of the object, okay, so the temperature of the object, so that's going to be constantly changing. That's going to be constantly changing. So that one we're going to leave as just t sub 0. So we have t sub 0. Sorry, that's a 0, not a 6. Over dt is equal to k times t sub 0 minus, now we are told that the temperature of the room, so the temperature of the surrounding, is kept at a constant 60 degrees. So that one we actually will plug in. Now at this point, this problem is very similar to example 2 in terms of finding the solution. In example 2, we had df over dt is equal to k times 900 minus f. So at this point, I would want you guys to try out and see if you can get this original solution equation on your own. After a little bit of work, you should get, I'm just going to skip some steps here, but you should get ln of the absolute value of t sub 0 minus 60 is equal to k times t plus c. And let's actually do this problem a little bit differently this time around. Let's actually do this problem with solving, getting t sub 0 by itself. So if you recall, remember the solution to this ends up looking something like this. So if we do e to the power of both sides, okay. So let's actually solve for t sub 0, get t sub 0 by itself. So this cancels out. the e and the ln cancel out. So we're left with t sub 0 minus 60 is equal to e to the kt plus c, which if you recall from yesterday's lesson, we can write e to the kt plus c as just c to the e kt power. And then we would just add 60 to both sides. So t sub 0 is equal to capital C e to the kt plus 60. All right. So you might be wondering, had you tried the same steps that we did in example 2, you might be wondering maybe why this time the ln does not have a negative in front. Well, if you tried u substitution again, if you did the integral or the antiderivative of both sides, if you did u substitution, you would have seen that if you made u equal to t sub 0 minus 60, the derivative of u this time around would have just been 1, not negative 1. So there would not have been a negative in front of the ln when you would have done the antiderivative. All right, so now we are told, let's solve for c. So we're told that the initial temperature is 100. So at t is equal to 0, the temperature is 100. So when t is equal to 0, temperature is 100. So solve, actually let me use a different color here. So we'll do orange. Solve for c. So at this point, so when t is equal to 0, the temperature is 100. So it's equal to ce to the power of, where was it, kt, so k times 0 plus 60, so 100, e to the 0 power is just 1, c plus 60, so c is equal to 40. 40 plus 60 is 100. All right, so t sub 0 is equal to 40 e to the kt plus 60. We still have to find what k is equal to. So solve for k. Let's do that now. So we have 100 is equal to, so c was 40. So 40e. To do that, we're going to use the fact that after 10 minutes, the temperature of the, what was it, the pastry? The baked cake was now 90. So actually, so now the temperature is 90. And this is after 10 minutes. I think we're using minutes. Yeah, we're using minutes for our, so e to the k times 10 plus 60. So subtract 60 from both sides. So 30 is equal to 40e to the 10k. Divide both sides by 40. So 3/4 is equal to e to the 10k. To get rid of e, we have to use ln. To get rid of e, we have to use ln, so we have to do ln to both sides. So ln of 3/4 is equal to ln of e to the 10k. The ln and the e cancel out, so all we're left with is just 10k. And to get the k by itself, we just have to divide both sides by 10. So ln of 3/4 divided by 10. That's our k value. So ln of 3/4 divided by 10. So let me rewrite it over here. So our new equation is 40e ln of 3/4 divided by 10t plus 60. And then finally, the last step of this question is asking us to find how much longer must Bernie wait to ice the cake. So we have to wait until it reaches 80 degrees. So at this point, we just have to solve for t when the temperature is equal to 80. So we have to solve for t when the temperature is equal to 80. Get that erased, okay. So when the temperature is equal to 80, we have 40e to the power of ln 3/4 divided by 10 times t plus 60. Get 60 to the other side, so subtract both sides by 60. So 20 is equal to 40e to the natural log of 3/4 divided by 10t. Divide both sides by 40, so 1/2. 20 divided by 40 is 1/2. E to the power of ln 3/4 over 10t. Do ln of both sides. E cancels out, so ln of 1/2 is equal to ln 3/4 divided by 10 times t. And then finally, to get t by itself, we just have to divide both sides by the quantity ln 3/4 divided by 10. So t is equal to whatever ln of 1/2 divided by the quantity ln of 3/4 divided by 10 is equal to. So plug that into a calculator. We should get our answer. All right, so let's see what we got here. So we have so ln of 0.5 divided by the quantity ln of 3/4, so I'm going to put 0.75, divided by 10. So you should get, if we round to 3 decimal places, 24.094 minutes. So that's how long it will take for the cake to cool to 80 degrees. So then that's the point in time when Bernie can finally ice the cake. All right. So just a couple of application problems here. You'll see that example 3 and example 2 were not very different from one another, including the equation themselves. They were very similar to each other. But in terms of the process, very similar. Being able to find the solution, which remember, you got to separate the variables. People separate the variables, then take the antiderivative both sides. In these cases, or at least in the problems today, we did solve for c. So we did find what that capital constant c was equal to. So that is today's lesson, day 4 of Unit 7. One comment I did want to make, or one regarding summatives, which I have graded, as hopefully you guys saw in the grade book. I have graded your summatives. Now what I need to do is what I would like to do is I would like to give you guys a chance to do corrections on the summatives. Now to do that, what I was thinking is, if you guys would like to do corrections on the summatives, please let me know. What I can do is I can scan, so just email me. I can scan the summatives, scan your summative. I can email that to you. Then you can do the corrections, send me a picture, do what you need, send it back to me, and I can put those into gradebook. So if you would like for me to send you the summatives, to scan them for you and send them to you so you can work on the corrections, please let me know. So just email me, let me know, and I'll do that as soon as possible. Otherwise, I will be posting some more extra practice for today's lesson. I hope you guys are staying safe. Once again, I will keep you guys as updated as possible regarding College Board. I hope nobody's gotten sick. And, I hope these days haven't been too stressful for you guys. I know most of you guys are seniors, and I know you guys are thinking about graduation. And I know CPS still hasn't provided any insight in terms of how any of those things are going to be working going forward. So hopefully you guys haven't been too stressed out. I hope you guys enjoy the rest of your day. Stay safe. Try to stay busy. Don't try to, bore yourselves to death. And I will see you guys later. Have a good one.